Welcome to this explainer. Today, we're decoding the hidden physics of a classic road trip. We're going to take something we've all experienced and learn how to read its hidden language. We're talking about decoding the lines, the curves, and those slopes that secretly govern every single move we make. Honestly, whether you're behind the wheel every day or you just want to understand the physics of the world around you, mastering these motion graphs, it's going to completely change how you look at a drive down the highway.
So to kick things off, I want you to picture this. You're cruising on the highway, and suddenly, brake lights just light up as far as you can see. You're stuck in stop-and-go traffic. It is super frustrating, right? But the brilliant minds over at Pasco posed this totally fascinating question about this exact scenario. What is the velocity of a car during stop-and-go driving? Like, are you actually moving? Are you stopped? How on earth do you even calculate your speed when it's fluctuating every 2 seconds?
All right, Section 1. Speedometer versus odometer. 2 ways to look at your trip.
To answer that traffic jam question, we really have to look at how we measure our trips. And we're not just talking about the dials on a dashboard here. These represent 2 fundamentally different ways of analyzing motion in physics. First up, we've got average velocity. Imagine you're taking a road trip from Houston to College Station. If you check your car's odometer to get the total distance you traveled, and then check your watch for the total time it took, you just divide that total distance by the total time and boom, you get your average velocity. But then, on the flip side, we have instantaneous velocity. That is the exact speed you are traveling at one frozen, specific moment in time. So if you glance down at your speedometer while you're cruising, that number right there, that's your instantaneous velocity. For that Houston trip, your average velocity over the whole drive might be 80 kilometers per hour, but your instantaneous velocity might be 100 kilometers per hour while you're actually driving, and a flat 0 while you're stopped getting gas.
And, this brilliantly illustrates how we read a position time graph. Think of the graph's curve almost like a physical landscape that you're hiking over. If you want to find your instantaneous velocity at any given moment, you just look at the tangent to the curve. It's actually really intuitive. If the slope of that tangent is steep, like a sheer cliff face, you are absolutely zooming. But if the slope is shallow or totally flat, your speed is barely a crawl or you've stopped entirely. It literally is that visual.
Moving on to Section 2, Decoding Acceleration Time Graphs, the landscape of speeding up.
For this part, we're pulling directly from some excellent instructional material over at Byju's. So instead of looking at our position or velocity, we're now plotting acceleration on the vertical axis and time on the horizontal axis. Take a look at this graph from the Arujuna JEE Physics Test Bank. Notice how incredibly simple it looks. It's just a perfectly flat, horizontal line sitting above the 0 mark. But what it actually represents is pretty thrilling. A flat line on an acceleration time graph means constant acceleration. In the real world, this is the equivalent of you stepping on the gas pedal and holding it perfectly, unyieldingly steady. Your speed is increasing, for sure, but the rate at which you're speeding up, that stays exactly the same. But what if you don't hold the pedal steady? Well, let's contrast 2 different scenarios here. In the first one, we've got an upward slope on our acceleration graph. This means you are pressing harder and harder on the gas pedal. Your rate of acceleration is actually increasing. Now, contrast that with the second scenario, a downward slope. This means you're easing off the gas. You are still accelerating, mind you, but the actual amount of acceleration is dropping as time goes on. Which brings us to Section 3, Finding Change in Velocity, the area under the curve.
Okay, this leads to a massive revelation. It's almost like a mathematical secret detailed in the BGU's text. How do we actually figure out how much our speed changed while we were accelerating? Well, the answer lies entirely in the area under the curve. Let me walk you through a fantastic example of a race car nearing the finish line. The driver starts to accelerate to finish strong, and the graph of her acceleration forms a triangle. So step 1, we just calculate the geometric area of that shape. Our basic formula for the area of a triangle is 1/2 times the base times the height, right? The driver accelerates for 8 seconds, so that's our base. Her peak acceleration is 6 meters per second squared, which is our height. So 1/2 times 8 times 6 equals an area of 24. What this actually means in physics terms is a change in velocity of 24 meters per second. Then step 2 is super simple. We just add that change to whatever speed she was originally doing.
So here's the absolutely crucial point. If our driver was originally cruising at 20 meters per second, and our graph's area tells us she added 24 meters per second to her speed, she blasts across the finish line at an incredible 44 meters per second. We found her exact speed just by measuring the area of a shape on a graph. I mean, how cool is that?
All right, Section 4, the concept of jerk, the rate of change of acceleration. Now, I kind of want to wake you up with one of my all-time favorite scientific terms, which is also introduced in the BJU's material. It honestly sounds like an insult, but it's actual physics. Jerk. By definition, jerk is the slope of the acceleration graph. It is literally the rate at which acceleration itself changes. Think about being in the passenger seat of a car. If the driver stomps on the gas pedal violently and abruptly, your head snaps right back against the headrest. That uncomfortable snapping sensation? That isn't just acceleration. It's a rapid change in acceleration. Mathematically, it's just the rise over run on our acceleration time graph. The steeper that slope, the bigger the jerk.
Let's move to Section 5, testing your graph knowledge. Put your intuition to the test.
All right, so you've absorbed a lot of theory today. Let's make this a bit more interactive and put your newly honed intuition to the test with a practical assessment drawn straight from the Pasco physics material. Here's the scenario. Kim is out for a workout. She runs at a constant instantaneous velocity of 3 meters per second for exactly 5 seconds. Then she stops completely and rests for 5 seconds. The question is, what is her average velocity over the entire 10-second period?
Let's consider our options here. Is it 5 meters per second? Maybe 3, 6, or 1.5? I want you to really think back to the difference between the speedometer and the odometer that we talked about earlier. Think about the total journey. Take a second and lock in your answer.
Okay, if you guessed 1.5 meters per second, you are absolutely correct. Remember, average velocity has to account for the total distance and the total time. In those first 5 seconds, running at 3 meters per second, Kim covers 15 meters. During her 5-second rest, her instantaneous velocity is 0, right? So she covers 0 meters. That means her total distance is 15 meters. Her total time, including that well-deserved rest, is 10 seconds. 15 divided by 10 gives us an average velocity of 1.5 meters per second.
So, let's bring everything we've learned together. Check out this complex velocity time graph from the Argentina JEE source. At the beginning, the line goes up. That's our constant acceleration. Then it goes completely flat at the top. Now remember, that doesn't mean they stopped. It actually means they're cruising at a constant instantaneous velocity. Then the line slopes downward, passing right through 0. That's them slowing down, stopping, and actually reversing direction. Just by understanding slopes, areas, and axes, you can look at these seemingly jagged lines and vividly imagine the exact physical story they're telling us.
And that brings us right back to where we started today. The next time you're sitting in the passenger seat, totally frustrated by endless stop-and-go traffic, I bet you won't just be staring blankly out the window anymore. You're going to be calculating exactly what's happening. Will you be thinking about your average trip on the odometer? Your instantaneous frustration on the speedometer? Or maybe the physical jerk of the car snapping you back and forth? The physics of the real world is constantly playing out right in front of us, beautifully graphed if we just know how to read it. Thank you so much for joining me on this explainer. Keep asking questions and keep looking for the science in the everyday.